name is Felix, and today we're going to be solving some physics questions. So, I apologize for the poor quality because none of this is scripted, and I'm just, like, improvising. So today we're going to be using kinematic equations to solve a problem regarding this. The Bombardier T1, which is the train used on line 2 Bloor-Danforth of the TTC. So, the question that we're going to solve today is, so if our final velocity of the train is 50 kilometers per hour forward, and the initial velocity, because it starts from stopped, is 0 kilometers per hour forward, and the actual acceleration, this is actual data from Wikipedia, the actual acceleration of this train is, that's an A. It's hard to write. The acceleration for this train is 0.85 meters per second squared. So we would like to find out how long did it take for the train to accelerate from 0 kilometers per hour to 50 kilometers per hour. So first we must convert the velocity into meters per second. So this 0 kilometers per hour is obviously the same thing as 0 meters per second forward. And how do I get rid of the screen line? And we'll have to do a little bit of trickery to convert the 50 kilometers per hour into meters per second. So here's a little shortcut conversion ratio you can use. You can simply do this. Since it'll be handy for kinematic problems on the test, because you'll be frequently converting from kilometers per hour to meters per second. And if you remember this will be a handy little shortcut. So you will have to multiply by 1 over 3.6 meters per second over kilometers per hour. Sorry if the writing's not clear, but there's an imaginary 1 like there, so you can just cancel that out like that. Then all we need to do is let me just make that decimal point more clear. All we need to do now is to take out our handy dandy calculator and calculate. So 50 dividing is the same thing as multiplying by 1 over something. So 50 divided by 3.6 equals 13.888888 and so on. So let's round it off to a few extra decimal places. We'll round according to sig figs in the end. So And now we will have to use a kinematic equation. So since for this one we want to solve for delta t, so we will want to use this kinematic equation since we know the variables VF, VI, and A. So let's do this. VF equals VI plus A delta t times delta t. And now we'll substitute in the variables. That's should have wrote it too close to the edge. 13.8889. I won't fit the units in. I'll put them below. Oh dear. VI, I can just write 0. Adding 0 does nothing. Let's not write it there to reduce clutter. Equals 0.85 meters per second squared. I forgot the direction there. It's forward. I forget that. Don't forget that acceleration is a vector quantity. I almost forgot that there. So that 0.85 meters per second squared forward times delta t. So now we divide both sides by we might have to move it over here a bit. I'm running out of room down there. So we just simply divide both sides by that. So it's 13.8889 meters per second. The directions won't matter later because time is a scalar quantity. Divided by 0. 0.85. I meant to write that. Per second. Squared. Forward. Equals 0.85 meters per second squared. Forward. 0.85 meters per second squared. Forward. Delta t. And now we just take out our handy dandy calculator once again. Just put it there. And punch it in. 13.8889 divided by 0.85 equals. There we go. The units cancel out. So that, because, yeah. No, wait. Yeah, that's right. So we divide by that on both sides, and, we're left with seconds, so delta t equals, I keep the calculator on top, that's a good question. Put it on the side. We'll round according to sig figs. We have the least amount of sig figs was, this has infinite sig figs because it's stopped. 2. So 2 sig figs. 16 seconds. And so we can finally put in our therefore statement. Might want to increase the font size of that. Therefore, I don't know how to type the therefore sign, but therefore, it took 16 seconds for the T1 train to accelerate from, it won't fit, let's just quickly shrink the font there, to accelerate from 0 kilometers per hour to 50 kilometers per hour. And there we go! A real-life application of the kinematic equations. Thank you for watching.